Okay, this is truly the last video on gases, and this is just kind of for information, I think. But it's kind of it's when I think of gases, I think about why understanding them is important with respect to chemistry. It's my mind immediately gravitates towards our atmosphere because it's very topical discussion. Number one, it's our atmosphere is a gas volume that's very important to life, and there's some interesting nuances to it. So I want to spend just a second about it. And the book actually has, I think, some pretty good sections here. It's towards the end of the chapter, but it talks about the Earth's atmosphere in terms of how it varies from ground level all the way up to where we meet up with space. And then it also talks about the composition of Earth's atmosphere, and then last it talks about the atmospheres of other objects in our solar system, other planets and other moons as well. So I want to make up just a few comments about all that. First of all, what I have here shown on the board is the essentially the mole fractions of a sample of dry air at I don't know, at standard conditions, at sea level under standard conditions. This is kind of what it looks. It's predominantly it's nitrogen. Probably it's in a almost a 4-to-1 ratio with oxygen. Oxygen is the second highest component, which, as you'll see when we look at other atmospheres in our solar system, both of these numbers are extremely rare. But having this much oxygen is incredibly rare. We don't see it anywhere else in our solar system. Okay, and then some of these other ones. Now, what I kind of want to point out is it drops off pretty rapidly after these first three components. Although I've left off water because what I said is that this is actually the mole fraction of dry air. So we actually had to actually artificially or intentionally remove all the water to come up with these numbers. Okay, well, if we didn't do that, what if we just took a normal air sample that was collected, let's say, over the ocean, but not under extremely humid conditions, but basically in a situation where we didn't actually go out of our way to prevent water from being there? How much water would there be? Well, it turns out it would water vapor would actually fit right here after argon in most conditions. I guess I guess under certain conditions, water could actually even pop up to be more prevalent than argon. But think of it kind of as roughly here. But it turns out it's way some than CO2. Okay, here's the only point I want to try to make here, and this is just sort of topical and might be useful in some conversations that you have, is that switching the attention to greenhouse gases, basically gases that act to insulate and basically keep sunlight that's absorbed from being radiated back out into space. We always hear that carbon dioxide is the most dangerous or most active greenhouse gas, and the amount of CO2 we have in our atmosphere is playing a significant role in terms of how much heat is being reflected back into space, essentially kind of keeping the heat in our atmosphere. In reality, they gloss over in almost any conversation. Whoever's talking about the subject fails to mention that the strongest greenhouse gas in our atmosphere is not CO2. It's actually water vapor. Water vapor is the most. It has the strongest ability to have this greenhouse effect of keeping energy from reflecting out into space, and it exists at dramatically higher levels than CO2. But of course, the amount of water vapor in the atmosphere kind of varies. It certainly varies with respect to elevation, and it varies across the planet based upon weather conditions and how much water, how much evaporation is going on of our oceans and all that jazz. But it is a very big component into calculating or modeling how our atmosphere behaves with respect to being able to hold on to its heat and in the atmosphere as opposed to reflecting it out into space. Okay, one thing I wanted to mention. The other thing I kind of want to talk about is, or look at, is turn to table, in my book it's table B5.2, and it basically has a list of planetary atmospheres. And of course it lists Earth's in there as well, according to these fractions. But just if you look at some of the other atmospheres, it's sort of interesting. For example, just quickly looking at Venus, you see that Venus's atmosphere is made up of almost entirely carbon dioxide. It's 96% carbon dioxide, has a little bit of nitrogen, and then it kind of drops off from there. Okay, and then if you look into some of the other, like Mars's atmosphere is very similar to Venus's, mostly CO2, a little bit of nitrogen. You can see in both those I mentioned that oxygen isn't really mentioned at all. Okay, but then I want to so the most prevalent gases in Venus and Mars happen to be a carbon-based gas that involves oxygen. So it's carbon and oxygen together. Well, if you look at Earth's atmosphere, sure, we have a really, really high oxygen content, and our planet has a very high carbon content as well. But remarkably, the concentration of carbon dioxide as compared to Venus and Mars is incredibly small. Why is that? Well, that's just a question to ponder. There's another aspect of this, which is if you look at Earth's atmosphere, and again, Earth has quite a concentration of carbon that makes up the Earth, but yet there really isn't any significant gas in our atmosphere that actually involves carbon, that contains carbon. I mean, CO2 at a pretty low level, and then it drops down into methane at an even lower level. Very little carbon. But again, you compare that with Mars and Venus, or even for that matter to Jupiter and Saturn, which they don't list the components there, but there is a higher concentration of methane gas in their atmosphere. And then even down into Titan, which is one of the moons of Saturn, Titan has roughly 2 to 5% methane in its atmosphere as well. But again, in our atmosphere, very, very, very little. So these are just kind of, I just want to point out that our atmosphere is pretty unique, and it's just at a glance anyway. It begs a lot of questions. Why so much oxygen? Why so little carbon-based compounds? Why so much nitrogen? Although you can look at, there's one other body in our solar system, which happens to be the moon of Saturn, that also has a very high concentration of nitrogen gas. 90% there. But here we have a pretty giant fraction of nitrogen as well. But again, you compare that to Venus and Mars, and both Venus and Mars have about 3% nitrogen in their atmospheres. So anyway, these are just kind of questions to ponder, but I think just kind of having an appreciation of our atmosphere a bit is worth knowing. So I want to spend just a little bit of time on that. Okay, I think that's it for Chapter 5.